And I'm going to pull up the handy dandy PowerPoint. And we are now. I did see you sent a couple of homework questions, Mr. Yap, and I think somebody else sent a couple. I will get to those next week because that way I've covered everything. After I cover everything, that's when I'll do the homework questions. So just work through as many homework problems as you can. And Monday and Wednesday of next week, we'll be going over homework questions depending on if I get through 11.2, which I don't think I'm going to today. But probability. Before we start probability, I'm going to go to my handy dandy. I'm going to give you a definition of probability, a Hubertism definition. Hubertism definition of probability is assigning, I don't know if that's supposed to be two N's or not, assigning a number between 0 and 1 to a prediction based on ... mathematics, logic, or experience. Help me out. Is there two N's in assigning or one N? It's going to bother me. I want to say there's two N's. I'm going to look it up right quick. I'd hate to have a... I'm not a speller by no means, but I believe there's two N's. I don't know. Assigning, A-S-S-I-G-N-N-I-G-N-G. There's only one N. I was right. Okay. Usually you go with your first choice. Assigning is just one N. Okay. All right. So and this is usually a decimal between 0 and 1. So between 0, 0.00 and 0.9999, you're putting, or between 0 and 1, you're putting a decimal assignment onto a prediction based on mathematics / data, which would mean stats, however you want to put it, logic, or experience. Now, why I tell you that, let's say you're on a two-lane road. There's one called Wild Hog Road in Anderson. And this is 24. And this is the double bridges. And this way is Townville. And this way is Anderson. And Pendleton's up here. This is Clemson Boulevard. The Waffle House is right here in Pendleton. So that gives you some direction of where I'm talking about. You get on Wild Hog Road, and it takes you 16 minutes to travel Wild Hog Road. But you get on Wild Hog Road, there's one problem with getting on Wild Hog Road. The problem is that when you get on Wild Hog Road, there's always a car in front of you that goes 33 miles an hour. And you can't pass on Wild Hog Road. It's about 15 miles or 12 miles, and it's hard to pass because it's just two lane, and it's just pretty straight road. So there's always traffic on it, and it's not easy to pass, okay? Even though it's straight, there's a lot of double yellow lines because there's so much traffic on it. And you get up to Pendleton High School. Pendleton High School is right here. You get up to Pendleton High School, and there's about a quarter of a mile between Pendleton High School and the red light. And before you get to the red light, you say to yourself, I bet you $1 that car in front of me that's going 35 miles an hour is going to turn left. And just as soon as you say that, they turn on their left blinker, and you have just predicted the future. Yes or no? Have you just predicted the future? No, you haven't. And I do this with all my classes. There is nobody that can predict the future. If anybody tries to tell you they can predict the future, all you got to do is ask them one question. What are the lottery numbers for the next Powerball drawing? Oh, well, that's not what I do. Well, yeah, that's right. You can't tell the future. Okay? All you got to do is ask anybody that can say they can tell the future. All you got to do is ask them one question. What are the lottery numbers for the next Powerball drawing? And of course they'll go, oh, well, that's not exactly what I do. No, you're a fraud. Shut up. Okay? You cannot predict the future. All right? Then how did I get that right? How did I know that? Well, first of all, I've been traveling that road first part of my career when I was at the Pendleton campus. I traveled that road 16 years, close to 16 years. No, close to 20 years, but I'd say between 15 and 20 years, I traveled that road going up to Pendleton. Okay? That's experience. All right? I live on the west side of Anderson. I live over here past, I live basically behind the Ingalls and behind the Bilo, back toward Sadler's Creek, about 2 or 3 miles back that way. So I live in this area right over in here, okay, back this way. So I traveled back and forth to Pendleton every day for 15 to 20 years, okay? What else do I know? Well, I also know that the only people that travel this road are either going to Pendleton, which is turn left, or they're going to Sandy Springs, which is turn right. Now, I know this woman is not going to Sandy Springs, logically. How do I know that? Well, I know it logically. Logically, that person in front of me is not going to Sandy Springs. How do I know that? Because if you know Wild Hog Road, you know that there's about 3 turnoffs that can go basically to Sandy Springs. Okay? So if this person was going to Sandy Springs, they would have turned right here, here, or here. So the logic tells me that this person is going to the left. So I didn't even use any mathematics here. I just used experience and logic, and I could tell the future. Okay? Nobody can tell the future. But what we can do is we can take mathematics, logic, and experience, and we can put a predict number on a prediction or a feeling and say, yeah, I think this is going to happen. And especially right now with the coronavirus, we're using statistics every day to try to find out where it's going to peak based on other things, okay? Based on other countries, based on past epidemics and growth and all that stuff. We're trying to find out when that peak is going to happen. Now, a lot of people got scared today because we've had over, I think it's 3,500 deaths or 3,000 deaths or 2,500 deaths, and everybody's freaking out. Well, we still have a mortality rate of 1.5%. Okay? That's the 9th lowest. There are 9 other countries that are in front of us that have a higher mortality rate. That means 8 other countries have a higher mortality rate. Okay, now the reason I'm telling you this is for a reason. All right? We're at 1.5%, and everybody's saying, well, we're number one. We have the highest cases. Yeah, but we got one of the lowest mortality rates. China, who we just passed as far as cases, has like a 5%, I think. I can't remember. I get the numbers mixed up. They have a 5% mortality rate. Iran has a 7% mortality rate. And Italy has a 9% mortality rate. And they're behind us as far as cases. So even though, and that's been there for a long time, our mortality rate has stayed at 1.5%. So what does that mean? That means that our cases may be going up, but the way we're handling it, as far as taking care of our people, giving them the whatever it's called, Quill and Z-Pack and whatever, monitoring them, putting them on ventilators, we still have the same mortality rate, even though the cases are higher. Okay, this is statistics. This is how statistics works. Now, we can take this data along with the 1918 data, along with the SARS data, and past coronaviruses, swine flu. We can take those rates, and we can try to predict when the coronavirus peaks. And when it peaks, that's when we can say, okay, everything's downhill from there, statistically. So are we telling the future? No. We're taking mathematics and logic, and we are predicting, putting a number on a prediction and saying, well, I'm pretty sure it's going to peak around this month or around this week or whatever the case may be. So we're using statistics every day right now, especially with the coronavirus. Okay, so let's go back to the slides. Well, if I can find my mouse. There we go. Sometimes my mouse has to wake up, I guess. Well, that's 11.1. And I've already covered a lot of this, so we'll be all right. What will you learn? Okay, I just gave you the definition of probability. Write this down. An experiment is controlled operation that yields a set of results. These are test questions, not on necessarily my test. I do think I asked that question about an experiment, though. And the other thing, I can't remember what I asked, but one is experiment. An observation. An experiment is when you have control. Okay? I'll write this down on my. An experiment is when you see the word control. When you see the word control in a definition, and your choices are experiment or observation, you go with experiment, because an observation, all you do is just watch. Okay, so I'll pull that up in just a minute when I get through writing. The possible results of an experiment are called its outcomes. The possible results of an experiment are called its outcomes. An event is a subcollection of the outcomes. So an outcome is what happens when you do an experiment. Okay? Result of the experiment. Experiment result. Let's say if it takes a mouse to go 10 seconds through a maze, then that's an experiment. I mean, that's the outcome. And then event is a collection of outcomes. A collection of outcomes. So that means if, let's say I did 10 trials of the mouse running through the maze, and I wrote down the times of those 10 trials, then that's an event. Those 10 trials, you put them together, that's an event. Okay? So that would be test questions right there. Again, I'm not going to ask very many test questions. I mean, not a lot of wording test questions. I'm going to ask more math questions than I am definitions. But I think there is a test question on there about experiment and observation. An experiment is when you control something, and an observation is when you watch something. Okay, so let's move on. Empirical probability is the relative frequency of occurrence of an event, and it's determined by actual observations of an event. So empirical probability is when you are actually doing the observation. All right, I'll give you an example. Let's say that you watch a mouse go through 10 trials of going through the maze, and you come up with an average time of 11 seconds. And then you take that data and you say, okay, I predict that he's going to take probably, and you look at the different times and you take the average and you find the standard deviation and you do all that, and you come up with, I believe he's going to take 10 seconds to run this next run. That's called empirical probability. You're taking data from your own you're using data from your own experiment, and that is called empirical probability. And I got another word for it. Empirical probability is what I call the physical probability. That'll make sense here in just a minute when I explain it. Actual, hands-on. Okay, I did the runs with the mouse. I timed them myself. I got the average. I did the mathematics, and I predicted something using my own experiment. That's physical probability. Theoretical probability is what I like to call the Mayberry probability. Mayberry is on the Andy Griffith Show, is a modern day utopia, even though it was filmed in the 60s. Modern day utopia. Everything's perfect. So theoretical is what I call the Mayberry probability. And the Mayberry probability is based on nothing but pure math. If I ask you, what is the probability of a king in a deck of cards? Well, you don't have a deck of cards, but you can tell me it's 4 out of 52. You don't have a deck of cards, so how did you find that probability? You found that probability because you know that there's 52 cards in a deck of cards, and you know there's 4 kings. But you don't have a deck of cards in front of you. So that's theoretical probability. It's based on nothing but what you remember about a deck of cards. Okay? So that's the differences between the two probabilities. And the empirical probability and the physical probability are the same formula. Okay? The number of something has occurred over the number of times it has been performed. Now you can easily translate that into okay, there's 4 kings in a deck of cards, and a deck of cards has 52 cards in it. So the number of times a king is there is 4. The number of times it could be is 52 because you don't know which one you're going to pick. So the number of times the experiment has been performed, there's 52 cards in a deck of cards. How many times something has occurred? There's only 4 kings. So that's how you always put the smaller number on the top. Okay? Same thing with a rolling a die. You know, dice, one dice is called a die. When you roll a die, you've only got 1/6 of a chance to roll a 6, or 1/6 of a chance to roll a 2, or 1/6 of a chance to roll a 1, because there's only 6 sides of the die. And if there's only 6 sides of the die, you can't go more than 6 on the denominator. Okay, so that's how you find the probability of an event. And this is the way that you write the probability of an event. Probability, parentheses, with a big E. Okay? Okay, here's an example. In 100 tosses of a fair coin, 44 landed on heads. What is the empirical probability? Why is it empirical? Because you are tossing the coin. It says in 100 tosses. Okay? And they're giving you how many times out of the 100 it is. Now, the probability of a coin landing on heads, or whatever, heads or tails, whatever they're asking, heads. The probability, the theoretical probability is 0.5 because there's only 2 sides of a coin. So this would come up 0.44, and what they're getting at is 0.44 is not equal to 0.5. And then they're going to talk about the large number rule of large numbers. 0.44 over 100, which is equal to 0.44. I'm sorry, 44 over 100, which is equal to 0.44. So that's the probability of heads. You could write this as the probability and put a capital H in there for heads. You could write the word probability, parentheses, heads, close parentheses. That really don't matter. But the number of times something actually happened over the number of times something could have happened. Now, what about the theoretical? The theoretical is going to be P is equal to, P of H is equal to 1 over 2, because there's only 2 sides of a coin, and there's one side that's heads. And that's where the 0.5 comes from. Okay. I'm not going to worry about these. We're going to skip through these. There's the law of large numbers. Now I want you to take a minute and write that down, because that's important. The law of large numbers states that the probability statements apply in practice to a large number of trials, not to a single trial. It is the relative frequency over the long run that is accurately predictable, not individual events or precise totals. Now that means absolutely nothing to y'all if you read that, but go ahead and write it down because it's important. You may see it on a standardized test. So, but I'm going to explain, I'm going to explain what they're saying in terms that you can understand. And I'm going to go to my handy dandy. So Mr. Yap, let me know when you finish writing that down, please.
Yes, sir. Okay, sir.
Okay, I'm going to write it down over here. The law of large numbers. And I'm going to exit here, pull this up. The law of large numbers is basically you have to increase the number of trials to get the physical probability to equal the Mayberry probability, or theoretical probability. What does that mean, Hubert? Well, we just said that 44 heads out of 100 flips is equal to 0.44 is equal to the probability of heads. That's called the physical probability because you actually did the flipping. However, there's one head, out of two sides of a coin, which is equal to 0.5, which is also the probability of heads. But that is the Mayberry probability, and this is the physical probability, and 0.44 does not equal 0.5. So there was a couple of students at MIT that actually took a roll of quarters, that's 40 quarters, and they took those 40 quarters and they measured them, they weighed them, they scanned them, they checked to see, they balanced them to see if they were balanced. They went through and did like 10 different measurements on those 40 quarters and got an average quarter dimensions from those 40 quarters. Now I'm talking to the 10,000th of a gram, to the 10,000th of a millimeter. They got those very, very finite, very, very small details. And they came up with an average quarter. They came up with an average quarter, and they put that quarter and made it an algorithm, created an algorithm of flipping with that quarter in a computer program. Everybody with me? So they just took a roll of quarters, and they took them and weighed each one of them, and they measured each one of them with a micrometer up to the 10,000th of a millimeter. And then they checked to see if they checked them with infrared beams or rays or whatever you call them. I can't think of the name right now. But they scanned them to see if they were balanced. They did all these different measurements, and they took the average of all those 10 measurements, and they came up with one quarter that was that weighed this much, that was this much in balance, that was this much in diameter, this thick. And they took those measurements and created that quarter in a computer program. And they flipped that quarter over and over and over until they got to 0.5, which is the Mayberry probability. Mr. Yap, you're the only person. Well, Mr. Dingler can't hear me. Can you still hear me, Mr. Dingler? Well, he still can't hear me. Mr. Yap, you can hear me. How many flips do you think it took for that algorithmically generated quarter to flip to get to the probability of heads being 0.5? How many flips do you think it took? Just give me
I'm going to say about 130.
130 flips? It took 100,000 flips
Wow.
to get the probability of 0.49999995. It took 100,000 flips to get a probability of 0.49999. Actually, it was like 10 nines, but you get the point. Okay? 100,000 flips. Now, why does that make a difference? Well, the law of large numbers basically says that you have to increase the number of trials of the physical probability to get the physical probability to equal the mathematical probability. Okay? Now, the law of large numbers, take that experiment and translate that into probability and statistics. We'll call it LOL, law of large numbers. Okay? The law of large numbers basically tells us in science, math, engineering, etc., we need to be capital S-U-R-E, that we have enough data before we can actually determine something. A conclusion. Basically, CYA. Do you know what CYA means, Mr. Yap? Cover your backside. Let's say you're in a real world situation. You're the quality assurance director for Michelin tires, and you work in that Crystal Palace up there in Greenville off 85, and you make $150,000 a year because you're the director of quality assurance for the Southeast Michelin plants. Okay? And your job is to work quality assurance numbers, and you have a meeting coming up that's going to predict next year budget bad tires. And you go, oh gosh, I got to get that meeting's next week. And I've been playing golf and doing this and doing that. Oh my gosh, I got to get a report together. So you go to the Sandy Springs plant, you go to the Anderson plant, you go to the Woodruff plant, you go to the Greenville plant, and you pick up 100 tires, and you check 100 tires on each one. That's 400 tires, and you do the math, and you come up with a defective rate. I say that the defective tires will be around 22%, which translates into $1.2 million for next year. Okay, so in the budget for defective tires, we need to count in $1.2 million for the 2021 budget. And everybody looks at you and go, "Oh, that's nice. You did a good job, Bob. Good job." Okay, and everybody pats you on the back. And next year rolls around, and before they do the predictions for next year, they talk about from 2020 to 2021, and they say, and we'll do this in red, they say that the defective tires was 52%, which means that it was 3.7 million. Now, Mr. Yap, I know you're not executive, but what do you think would happen if you predicted $1.2 million and you showed up at the next meeting the next year and the actual deficit or the defective rate was 3.7 million, what do you think would happen?
You'd probably get fired.
You would get fired. Why? Because we're not talking about saying a bad word at the water fountain. We're talking about costing Michelin what? 1.5 or $2.5 million. Somebody's going to lose their job because of that. Now, why did Bob screw up? Well, he only pulled 400 tires. I don't know how many of y'all know anything about Michelin, but 400 tires, Michelin can do 400 tires in 3 minutes. Okay? 400 tires is nothing to Michelin. All right? They should have pulled thousands or 10,000. We're talking about the whole year. Let me know how many tires were defective over the whole year. So you need to pull a big amount. If Michelin, let's say the Sandy Springs plant puts out 600,000 tires a year, well then you need to get a bigger sample than 100. Okay? That's what the law of large numbers tells us. No matter what you're doing, whether you're in science, whether you're in math, whether you're in engineering, or a student, if you've got a job to do, if you've got an assignment, you can't suffer from LAD. You need to actually get out there and do the work. You cannot improvise and just go out and pull 100 when you're talking about one of those plants putting out 600,000 tires a year. So you got to think about it. I hope I'm not going over. Let's see. I thought I heard the music go off. Did I? Yeah, I think it's, what time's class over? 1:15? Yes or no?
Yes, sir, I think so.
Okay. All right, we'll go ahead and shut her down right now. I didn't think I'd get through the whole unit anyway. I meant the whole section. So that means we're going to have to work on 11.1 on Monday also. So y'all keep working on the homework, and we will finish 11.1 on Monday. Okay?
Okay, sir.
Okay, you got any questions?